This is the last section of 1.3 or 1.5. So part 3, graphs of functions. And really what we're going to get out of this section is there will be some review of things that you've already learned, but it really is the big part about 1.5 that is a segue into what calculus will start doing with the graphs of functions. So hopefully we're going to get something out of this that will get you prepared for calculus whenever you take that. So the essential question is what types of graph specific characteristics are important for functions. And what we're going to do is we're going to learn specifically in this section, we're going to determine intervals on which functions are increasing, decreasing, or constant, very important. And we're also going to be able to determine maximums and minimums of functions. So let's just get right into it. So we're looking at this graph here, and you see on this top here, it says always go left to right. So basically, we are going to discuss how do we know when a function is increasing and decreasing. So keep in mind, increasing and decreasing is another word of saying positive slope and negative slope. And I think that all of you can look at a graph and see where there's a positive slope and where there's a negative slope. And of course, a constant increasing, no increase or decrease would be a zero slope. So positive slope is increasing, negative slope is decreasing, and zero slope is constant. So when we look at a graph, we should be able to say the intervals where a function is increasing. So right here, this is where our function is increasing. With this arrow, it means that we are going from negative infinity. So negative infinity to, it looks like negative 5. Okay, we're going to say to negative 5. Now, because there's a change over there, we're not going to include the negative 5. It's increasing until negative 5, and then it's kind of changing. And then it's going to be constant, in other words, a zero slope, from, it looks like negative 5 to 0. So we're going to say from negative 5 to 0. And then it's decreasing from 0 all the way to negative infinity. Or sorry, positive infinity. And that's pretty much it. So you should be able to look at a graph and be able to determine when the graph is increasing and when it's decreasing. So we've got a few different things to look at on your paper here, and this is a lot of definition stuff, but we'll just go through this very, very quickly. So a function's increasing on an interval if and only if for 2 points a positive change. Basically, it's only increasing if the slope is positive between 2 points. Okay, it's decreasing if the slope is negative between 2 points, and it's constant if the slope is 0 between 2 points. That's basically the layman's terms of putting it, but this is actually words and symbols. We don't have to worry about this too much, but I wanted to make sure that you were aware of this and you had access to this, just in case you see some terminology that you're not familiar with. You can maybe go back to this. So maybe jotting down what I just said would help. Increasing means it's a positive slope between 2 points. Decrease, negative slope between 2 points. Constant, zero slope between 2 points. And then maybe you can kind of transfer the lingo that they're using with what I just told you. Okay, so let's take a look at this. So we have a function here is a parabola, and we want to know when it is increasing, constant, flat, and decreasing. So in this case, we look at increasing. So hopefully you can figure out that it's increasing from this point down here all the way to positive infinity. So it looks like from 0 to infinity it's increasing. Decreasing, hopefully you can figure out it's going from negative infinity to 0. And it's never really flat. I mean, maybe you could say it's flat at 0, but there's really no interval there. So if we wanted to say from 0 to 0, we could say that. Okay, that just means that 0 is included. So maybe you just say equals 0. You don't even have to necessarily say this. You could just say at 0. It's flat, because it technically is flat there because it's changing from decreasing to increasing. So if it's changing from decreasing to increasing, meaning if it's going from a negative slope to a positive slope, there's got to be a 0 in between there. Okay, moving on. Okay, let's talk about this. Okay, so here we're going to approximate. but from increasing. So I see, okay, we have a graph that's decreasing as we go down, and then it looks like right around here, it looks like it starts to increase. And we're going to approximate these, and that's okay. And then it looks like it increases to about there. So I would say from, let's say negative 0.5 to positive 0.5. And then decreasing, we know that it goes from negative infinity, because of the arrow, to negative 0.5. So negative infinity to negative 0.5. And we're going to union that with, it decreases again from positive 0.5 to positive infinity. Now again, if we wanted to say where is it flat, well, we could just say at negative 0.5 and positive 0.5, because that's where it would have to change from negative to positive, so it has to hit 0, and it has to change from positive to negative, so it has to hit 0 again. Now that's not really flat, but we can still consider those flat points. Just at one individual point, there's just no interval there. And we can say x equals if we're that worried about it. Okay, so now let's talk about some different terminology about a graph. So we've just talked about where things are increasing and where they're decreasing and where they're flat. So specifically, we're talking about the slopes of those graphs, essentially. So it says, while graphical approach to identifying the intervals on which a function is increasing, decreasing, or constant can be supported numerically, typically, calculus is often needed to truly confirm these numbers. So we have a couple of terms here that I think are important. Extrema. Extrema are called critical points in which a function changes its increasing or decreasing behavior. So maximums or minimums. So if you go back and you see what we just pointed out here, we have a little bit of a minimum here and a maximum here. So we call that a flat point, but really it's called an extreme point or a critical point because this is a minimum and this is a maximum. So that's what we consider. So notice how it changed from increasing to decreasing or decreasing to increasing. That's what we call maximums or minimums. We consider those extrema. Now, points of inflection are a little bit more difficult because you've never seen this term before. Points of inflection are points where the graph changes its shape. So it goes like from bent upward to bent downward. So looking at this, we would call this bent upward. Okay, and as soon as, and it's still bent upward, and then somewhere right around here at this point, instead of it being bent upward, it's now kind of curved or bent downward. That is what we call a point of inflection, where a graph changes how it's shaped. Now, you also call this concavity, this right here. So this is also called concavity. So when we say bent upwards, that's called concave up. Actually, let me write this on the other one. So we're going to say bent upward, we call that concave up. And bent downward is concave down. Okay? So let's kind of look at a couple problems and see how this works. So here, we look at this graph, and we're going to make some corrections on this graph too. But so we have a minimum. The minimums and maximums are really easy to see. But again, what you want to notice is a minimum. Yes, it is a low point in this area of the graph. But it's also where a graph changes from a negative slope to a positive slope. Okay, it's a turning point. Okay, and then over here we have our maximum. We change from a positive slope to a negative slope, and in the middle here we have this point of inflection. Well, yes, this point of inflection is true because we're going from concave down. You see how it's curved down right here, and then it changes to curved upward. But also we're missing a couple here because I would argue that there's also a point of inflection right here because if you notice we're actually going concave up, bent upward to bent downward. So that's still a point of inflection. And then also, we're going to have a point of inflection probably right around here because we're going from curved upwards or bent upwards, concave up, to concave down. It should be really easy for you to see the change in the shape of the graph. Maybe it just takes a little bit of time for you to get the lingo down on that. So, but understand there are 3 points of inflection here because there are 3 changes in what we call concavity. Okay? So let's look at an example actually, there's a chart here. So let's talk about some more terminology. So relative maximum. Relative maximum refers to a local area on the graph where we have a maximum. So like on your paper, you can see there's a maximum here. There's a maximum over here. So those are local or relative maximums. Okay? Now, what happens about, what's the difference between a relative maximum and an absolute maximum? An absolute maximum is going to be the highest point on a graph. So like over here, in the model, the higher maximum, even though it is considered a relative maximum, it would also be considered an absolute maximum because it is the highest point on the graph. And the same thing can be said about the relative minimums and the absolute minimums. Relative minimums are relative, so relative, relative. But the absolute minimum would be this point right here because that is actually the lowest point on the graph. Okay, so when we're looking at this graph right here, we're just going to estimate. We don't have to have anything perfect right now. Let's just estimate for this purposes. So let's talk about the extrema. So extrema, remember, are maxes and mins. Okay, so maximum, minimums. So maximum, we can look at this point right here. And we can say that looks like it's at x equals -1/2. So that's where we have a maximum. Okay? Then we have minimums. Well, minimum looks like it's at 1 approximately. So we're going to say x equals 1. Okay, now if we want to talk about points of inflection, so we can call these extrema, but really they're just critical points. But there's no real direction here to do points of inflection, but let's talk about that. So points of inflection, we can approximate it. So we have a graph that looks like it's concave down going all the way through, and then it looks like at maybe right around this point right here, maybe about x equals +1/2, we get a change. It goes from downward to upward. So our point of inflection here would be x equals 1/2. Point of inflection at x equals 1/2, maximum at x equals -1/2, and the minimum at x equals 1. Okay, what I want you to do, and this actually went a little bit quicker than I thought it would. What we're going to do is I want you to do this one on your own. Instead of you taking a little quiz on Edpuzzle, what we're going to do is we're going to wait until class tomorrow. We're going to do this first thing as our do now. So I want you to do this on your own. Use your graphing calculator or graphing tool, Desmos, to estimate and classify the extrema. So I want maxes, I want mins, and I want points of inflection. Okay, so just make an approximation. It doesn't have to be perfect. Okay, so do that, and I will see you in class tomorrow.